Welcome to the next installment of Lecture 2E, where we're going to talk about the solubility of gases. Now, we're going to refer to solubility, temperature, and pressure kind of as an STP, but not the standard temperature and pressure that we've used STP for earlier. Here we're going to talk about solubility, temperature, and pressure, and how solubility is affected by both temperature and pressure. So we've looked at solubility a little bit with solids, or you may have done so in a previous class. And for solids, you know that as the temperature of a solution increases, the solubility of a solid also generally increases. It's not a 100% rule by any means. There are situations where it goes the other direction. But a good general rule for solids is as temperature increases, solubility also increases. Now for pressure, solubility of a solid is pretty much not affected by pressure one bit because you can't compress your solids, and so pressure has essentially no effect on solids or their solubility. Gases, however, are affected strongly by both of these conditions. So as temperature of a solution increases, the solubility of a gas dissolved in that solution decreases. And so it's exactly opposite of what you would expect for solids. So as temperature increases, solubility decreases for gases. And in contrast to solids and pressure, we saw that solubility is not affected by pressure for solids. However, when you increase the pressure on a gas, the solubility increases. And so both temperature and pressure greatly affect the solubility of a gas in a liquid. So, something's afoot. Oh, look, it's a foot. So if we're looking at gases in solution, we're going to look at something called Henry's law, and that's primarily deals with pressure. So Henry's law states that the solubility of a gas is proportional to the gas pressure. It's a nice, simple equation. So we have Sg, which represents our solubility of that gas in terms of molarity, so moles per liter of solution. We have the Henry's law constant, Kh, so K for the constant, H for Henry. It's a very gas-specific constant, so it's something that's tabulated. It's something that you have to look up for a given temperature. And then you've got your Pg, so it's pressure of the gas. So it's the partial pressure of that gas. Usually in bar, you may see it in atmospheres, depending on what your Henry's law constant is given in. So you'll want to look at the pressure units of your Henry's law constant that you look up, and that's what you need to express the partial pressure of a specific gas. So either bar or atmospheres or millimeters of mercury or something like that. So some examples of where this takes place. We have carbonation. So if you have a carbonated soda that's fizzy, that's dissolved carbon dioxide in that water. And there's a reason why when you unscrew the cap, it goes, and that's because it's under high pressure. You have to increase that pressure over that solution in order to dissolve that carbon dioxide. When that pressure is lowered, so if that pressure goes down, well, the Henry's law constant is a constant. And so if you lower the pressure over that solution, your solubility is going to go down and some of that gas has to leave that solution. And so that's what happens when you open the cap on a soda, is you release the pressure and you decrease the solubility of the carbon dioxide in the water. And so some of that carbon dioxide must come out of the soda. If you're familiar with the idea of the bends, which is a condition that can affect the scuba divers. So what causes the bends is if you are diving fairly deep, you are breathing in through your scuba equipment, you're breathing in compressed gas, and it's under a high pressure because for every roughly 33, or let's see, I got to go metric again, 10 meters of depth in the water, you increase the pressure on your lungs by about a single bar. And so you basically double your atmospheric pressure, or you add an additional atmosphere's worth of pressure every 10 meters that you go underneath the water. And so what that increase in pressure does then is it increases the amount of pressure in your lungs, and it changes the solubility of all those gases that you're inhaling. And so if you have strictly just compressed air that you're breathing in, which you normally would for a regular dive, that's going to include a lot of nitrogen. And so the nitrogen is also going to dissolve into your bloodstream. Nitrogen is not very soluble in your bloodstream, and so you're forcing it out. Now, when you come back up from your dive, you have to stop at certain areas, certain depths, and just sit there and wait for a while. And the reason you have to do that is because as you go back up to the surface from a dive, the pressure on your lungs is now decreasing, and that solubility of the nitrogen is also decreasing, and it's going to start forming little bubbles in your blood. And those bubbles are going to work their way back to your lungs, and you breathe them out. However, if you come up too fast and you don't make stops, those bubbles get really big and they can even burst. And so you can suffer some kind of brain aneurysm. You can burst veins and arteries all through your body, and you can put yourself in a pretty bad state. And so that's what creates the bends. You can go kind of opposite if you go too high in elevation, where you don't have a very high partial pressure of oxygen on your body. So if you go climbing a really high mountain without preparing yourself, and your body's not used to operating in low oxygen, you get what's called altitude sickness, because your body says something's not right here. I don't have enough oxygen that I normally use to function, and your body just chooses to feel bad. And so that's called altitude sickness. Again, that lower partial pressure, there's not as much oxygen available. It's not as soluble in your bloodstream, and so you're not going to get as much oxygen to help your brain run. So here's just an example of how carbonation might be formed. If you have a certain amount of gas here, and you've got some gas dissolved in here, it is going to be in equilibrium in a closed system. That's why a fresh bottle of soda is really hard to squeeze. You actually have a fairly high pressure in that small space above the surface of the soda, and it's keeping that carbon dioxide dissolved in the soda. But it is at equilibrium. There's going to be carbon dioxide molecules coming out, carbon dioxide molecules coming in as they collide with the surface. If you are to push down on that piston, so we're putting a great pressure onto that liquid there, or onto the gas, then what you're doing is essentially creating more collisions with the surface of the liquid, because there's less space for them to move, and you're going to force more gas molecules to be dissolved in that solution. And then once it gets to a certain point, it'll restore an equilibrium with, you'll have fewer gas molecules in this space here, but you'll have a greater number of gas molecules down in here. Thus, you've increased the solubility of that gas in the liquid, because there's now more moles of gas in the liquid than there was at a lower pressure.